Welcome to Artificial Intelligence in Education, AI, and Human Perception. The lecture will start out by providing you with a short introduction and learning outcomes. Then we'll move on to discuss human visual perception, machine intelligence and computer vision, and then close. This lecture details the processes involved with human perception and how this relates to machine intelligence and computer vision. A number of limitations pertaining to computer vision are discussed prior to introducing how image recognition occurs in a neural network. Aspects of training machines to recognize what they see are explored, and an opportunity to train a machine is presented. The learning outcomes are three. 1. Understand the role that perception plays in artificial intelligence. 2. Identify how a machine develops a neural network for image recognition. And 3. Articulate the impact of AI on industries and the importance of understanding AI for students and educators alike. Human visual perception. Perception is a process of acquiring, interpreting, selecting, and organizing sensory information. As humans, we find this natural and generally very easy. Well, perhaps we think that we do. Engage with the following perception exercises to see how well you go. How well do you think an AI system might go with the same exercises? What do you see in perception exercise number 1? Do you see a duck or a rabbit? Perhaps both. Maybe now that you know what to look for, you might be able to see that which you did not see previously. Now consider perception exercise number 2. Are these images both of bagels? Are they both dogs? Did these images fool you, or is it common sense to be able to recognize animals from food? What the optical illusions in these two exercises illustrate is that human perception is the result of specific computations taking place in the brain. Although we are not conscious of these computations, we can sometimes get a glimpse of the process by examining cases where the computational process yields surprising or misleading results. Such optical illusions as that presented in Figure 4.3 also demonstrate that among humans, how you interpret things can lead to age biases. In Figure 4.3, you might see a younger woman who is turning away, or you may see an older woman looking toward the left. However, if you are younger, you will tend to see the young woman first, and vice versa if you are older. To understand the science behind perception further, you might like to read the article "Reality is Not What It Seems: The Science Behind Why Optical Illusions Mess with Our Minds." And there's a link to that on screen, along with a link to the article on age bias. You can look at both of those in your own time. Machine intelligence and computer vision. Machine intelligence includes learning, reasoning, perception, problem-solving, and linguistic intelligence. Machine perception aims to replicate the ability of humans to understand their surroundings. It involves such technologies as image and speech recognition. In the field of computer vision, machine learning models learn how to identify objects, people, or individual attributes in an image. For example, a model could help evaluate automobile accidents, identify the type of vehicle or vehicles involved in the accident, and provide an estimate for repair costs. Computer vision may involve aspects of edge detection, facial recognition, image classification, image segmentation, object detection, object tracking, and pattern detection. These aspects are all detailed in Table 4.1. Here we can see that edge detection involves identifying the edge of an object or environment to help identify what is in the image. Facial recognition includes recognizing a human face and identifying the actual person. Image classification involves sorting images into different categories. Image segmentation looks at separating an image into multiple areas and analyzing them separately. Object detection concerns recognizing and classifying a specific object in an image or multiple objects in an image. Object tracking concerns using object detection, following images as they move from frame to frame. And pattern detection really looks at finding patterns related to color, shape, objects, faces, and other visual features in images. Taking Table 4.1 into account, answer the succeeding question in the associated workbook. Workbook Activity 4.1. Question 4.1. From the following, how does computer vision identify an image? A. Computer vision technologies break down an image into smaller components and use deep learning neural networks to analyze each component before it identifies the image. B. Computer vision technologies label images based on training data and then breaks the image into smaller components to see if its label is correct. C. Computer vision technologies organizes parts of an image into various categories and then calculates the most common category found. D. Computer vision searches for a perfect match of an image from a large database of images. Take 3 minutes to record your answer. You would be correct if you chose B. Computer vision technologies label images based on training data and then breaks the image into smaller components to see if its label is correct. Real-world applications. Computer vision has a number of real-world applications across all sectors, from business, entertainment, transportation, healthcare, and in everyday life. For example, agriculture. Here, it can analyze crops for optimal growth, for example, in data-driven farming. View, for example, FarmBeats tracks soil and moisture data 24/7. Education. Eye tracking is an excellent way to study visual attention and social interaction in a number of learner settings, along with visual perception in teaching and learning. And such things such as lexical lookup and reading rates in EFL contexts. You might like to view language proficiency awareness through eye movements. Entertainment. Manipulate photos and videos in real time with filters. Automatically tag photos and videos, as well as upscale photo and video assets during the editing process. See further examples from within computer vision for media and entertainment. Shopping. Try on items virtually before purchasing. Use computer vision to predict future fashion trends or track items that consumers take from shelves in autonomous stores. See, for example, computer vision-powered autonomous store. Healthcare. Analyze X-rays and other scans to monitor patient health and to help doctors diagnose diseases. See also computer vision in healthcare and medicine. Self-driving cars. Identify other cars, traffic signs and signals, lane markers, pedestrians, bicycles, and other relevant visual information encountered on the road. Consider watching machine learning ride in self-driving car. Traffic. Oversee busy intersections for potential accidents and record license plates at road toll stations. Perhaps view traffic surveillance with computer vision and deep learning. Translation. Point a smartphone camera at text in another language and have it instantly translate. Consider watching the lecture, Sign Language Translation with Transformers. Manufacturing. Monitor equipment for safety and count and categorize items on a conveyor belt. View, if desired, the power of computer vision in manufacturing. Real-time sports tracking. Analyze player performance and strategy, like with a smart soccer ball, such as the Dribble Up Smart Soccer Ball. Limitations. With all of the amazing things that computer vision is capable of, there are still some limitations. These include 1. Interpretation. This is difficult for machines. AI systems that use computer vision must make sense of the complexity of our world and all of its variations, and this remains a huge challenge for machines. 2. Black box algorithms. It is difficult to decipher all of the inner workings of computer vision technologies, and like other deep learning applications, if something goes wrong, there may not necessarily be an easy way to understand why. 3. Big data. Computer vision, like other forms of AI where machine learning is involved, requires a lot of data to ensure accuracy of results. The data must be representative of many different contexts, angles, variations, and other scenarios in the real world. If a machine is presented with an image in a way that it is not being trained on, the machine will have some difficulty identifying the image. Let's turn to Workbook Activity 4.2 now. Here, you're going to spend 10 minutes to explore a variety of computer vision systems, and spend a few minutes with each of them. Then, answer the questions in the associated workbook. So the computer vision systems that you should be looking at are A. Draw together with a neural network. B. Shadow art. C. Emoji scavenger hunt. And D. Deep dream generator photo manipulator. And the questions that you need to respond to are 4.2a. Which of these systems impressed you the most? And question 4.2b. What do you feel are the implications of such a system? Take 10 minutes now and go and do that. Image recognition in neural networks. The following example illustrates how a neural network undergoes the process of image recognition for the purposes of training. In this example, the machine learns how to identify cats by analyzing example images. This is undertaken by the neural network without any prior knowledge of cats. Instead, the neural network evolves its own set of relevant characteristics from the learning material as it is processed layer by layer. Training data example. In order to provide the neural network with visual data to identify a cat, 5 layers are provided. See figures 4.4 through 4.8. Now, progress through each layer, reviewing the questions and determining the answers. This will assist you in completing workbook activity 4.3. Layer 1. What do the images on the left have in common that the images on the right do not have in common? A. They are all amphibians. B. They are all mammals. C. They are all animals. Layer 2. What do the images on the left have in common that the images on the right do not have in common? A. They all have ears. B. They all have stripes. C. They all have 4 legs. Layer 3. What do the images on the left have in common that the images on the right do not have in common? A. They all have feathers. B. They all have eyes. C. They all have fur. Layer 4. What do the images on the left have in common that the images on the right do not have in common? A. They all have teeth. B. They all have chins. C. They all have whiskers. Layer 5. What do the images on the left have in common that the images on the right do not have in common? A. They all have numbers on them. B. They all have eyes. C. They are all smaller than a laundry basket. Let's look at workbook activity 4.3 now. So you've just reviewed 5 layers of training data, experiencing essentially how a machine might learn what a cat is in order to identify it and distinguish it as cat or not cat. So now, complete the associated table in the workbook by answering the following questions. 4.3a. What is the training data that emerges and the associated rule for determining what a cat is for each layer? Question 4.3b. How does this neural network ultimately determine if something is a cat or not? Write out the algorithm that it will use. Go ahead and take 5 minutes to do that now. Hopefully you were able to provide similar responses to the workbook activity as those found in Table 4.2 here, and that your algorithm reads along the lines of, if an animal has 4 legs, has fur, has whiskers, and is smaller than a laundry basket, then it is a cat. Okay, so let's turn to workbook activity 4.4 now. And since you know what a cat is or is not according to the training data, taking on the role of a neural network, utilize the algorithm from workbook activity 4.3 to complete workbook activity 4.4. And the question is, 4.4, examine each image A through D, then answer the 4 questions next to each. Use that criteria to determine how you will identify each image. Is the image cat or not cat? Take 5 minutes to go and do that now. According to the training data, your responses should indicate that A and D can be identified as cat, while images B and C can be identified as not cat. From this activity, we can see that training data and the associated algorithms used by neural networks can lead to machines making mistakes. However, as these machines are trained with more and more data on what is right and wrong, they can become increasingly accurate. Training a machine. It's your turn now to train a machine to test the capabilities and limitations of the technology. You can experiment with different classifications or image data and take note of how the machine responds. This will deepen your understanding about how machine learning and computer vision work. In order to do this, you will need to develop a project with the teachable machine, and a link to that is provided on screen. Before you begin, you will need to understand 4 steps. 1. Gathering samples. 2. Training the machine. 3. Exporting the model. And 4. Hosting the model online. And there are URLs on screen that you can go to help you understand these things. Now, understanding these things is important because you will need to create one of the following project types. And that is either A, an audio project, B, an image project, or C, a pose project. Now, the site will guide you in the process, but you may like to begin with one of the following teachable machine tutorials to help you understand the kind of projects that can be developed. And these are A, fruit, B, head tilts, and C, sounds. Once you have completed your project and exported it, you can then answer the following in the associated workbook. Question 4.5a, what was your teachable machine project choice? And question 4.5b, what is your project link? In closing, from this lecture, you learned that computers have no innate perceptual abilities. Everything must be programmed or trained. Training data can lead machines to make mistakes, but with more input they can gain accuracy. There are a number of ways to train a machine, and what it is like to develop a project in order to train a machine. I would like to thank you for taking the time to listen to this lecture. I trust that you found it interesting and worthwhile, and have learned something in the process. Thank you.